Welcome to Radiochemistry 702. Today we'll have the introduction presentation. The readings that go along with this introduction presentation are the chart of the nuclides, front part of the chart of the nuclides. You should all have a copy of that, and the table of the isotopes. You can download the table of the isotopes at the URL that's listed here. When you are complete with this presentation, please provide some input into the blog. The blog URL is listed here. It's also provided on the web page. Just looking for some comments. If there's any questions, these questions can be answered, or statements that you've just completed the lecture. Okay, what we'd like to talk about today is listed here: the organization of the class, the outcomes, what we expect you to get out of the course, and the grades, description of the chart of the nuclides and the table of the isotopes, and then an introduction to radiochemistry. Okay, the outcomes, what we expect you to get out of this course, are listed here. Primarily issues related to the chemical properties of radiation radiochemistry, how thermodynamics and chemical kinetics can be used to evaluate radionuclide speciation. Speciation, the chemical form of radionuclides, is going to be a very important component of this course and eventually your research. Since these isotopes we're evaluating are radioactive, you may need to have an understanding of how radiolysis plays into the chemistry of these radioisotopes. Nuclear reactions drive isotope production, so you should be able to understand something about how to evaluate nuclear reactions. And once reactions occur, you will need to understand something about radiochemical separation. So we'll discuss radiochemical separations in some detail. And then finally, we should be able to understand how radiochemistry can be used to evaluate chemical behavior, and from this, how it impacts research.
The grading for the class is presented here. The PDFs at the end of the lecture are worth 5 in total. Please send these directly after you've completed the blog of the lecture. They shouldn't take more than 10 minutes. Quizzes, worth 12.5% each, are take-home quizzes and include tools that you can use for your research, for instance, spreadsheets for calculating concentrations or activities. At the end of the course is a presentation, which is worth 20% of your grade. This is based upon recent literature, is an oral exam, and is designed to prep you for the oral exam for the advancement to candidacy. This will be about 20 to 25 minutes. And participation is also ranked at 12.5%, similar to a quiz. And this participation is from blog responses, Skype meetings, or in class with Frederic. The goal of this class is to develop and assist your research activities in the UNLV radiochemistry program. Here's listed an outline of the course, which has been emailed to you and is also on the web page. Of note are wherever there will be a meeting, it's listed here, the topic, and these meetings will primarily be with Frederic. If this schedule needs to change due to travel, we will notify you by email, and the change will be noted on the blog, in addition to Frederic letting you know that these changes have occurred.
Okay, let's introduce radiochemistry. For me, one of the ways to define radiochemistry is the intersection of the chart of the nuclides, which describes nuclear properties, and the periodic table, which is based upon electron properties. This means that within radiochemistry, we're interested in both the electron properties, how we can manipulate the chemistry, and the nucleus. What does that do for us? How we can determine things about the nucleus, how we can utilize those nuclear properties for different technologies. Other thing with radiochemistry, there are certain elements which are only available as radioactive isotopes, the radioelements. These are examples of these are technetium, promethium, the actinides. Radiochemistry naturally lends itself to exploring the chemistry of these elements. Okay, so when we think of an atom, there's two components that when we look at it, we can break it down to two components that are involved in radiochemistry: the nucleus and the electrons. The nucleus, a very small part of the atom, contains the Z number of protons and the number of neutrons within that nucleus. We actually use this to define the isotopes that we're interested in. The electron interactions, well, we understand those from chemistry. Those define the chemical properties, and those extend much further out than the nucleus. The the nuclear properties, the number of the protons and the neutron, that actually helps us define some terms that we use in radiochemistry. And some of these terms are listed here: isotope, isobar, isotone, and isomer. Isotopes, well, those are the same elements with different numbers of neutrons. So the Z is the same, N changes, carbon-12, carbon-13 is an example. An isobar, well, that's the sum of the number of neutrons and protons is the same, but the number of neutrons and protons change. So, for instance, the A of 99 isobar, undergoing beta decay, those excess neutrons will be converted into protons. So you will have the sum of the number of neutrons and protons being the same, but the actual number can change. An isotone, which is used in evaluating some nuclear properties, has the same number of neutrons but different number of protons. And an isomer, which is an excited nuclear state, is usually defined by an M. So that's very widely used in nuclear technology for radiopharmaceuticals, is technetium-99M, M being the metastable state. Okay, radioactive decay. There's some common radioactive decays that are listed here. There's a full list in your table of the isotopes. Alpha, beta, well, alpha decay, where a helium nucleus is emitted, usually happens in the heavier isotopes. Beta decay, the emission of an electron, where the conversion of a neutron into a proton, building up the periodic table. Positron emission, well, that's where a proton is actually converted into a neutron with the emission of a positron, which is the antimatter pair of the electron. Electron capture, where the nucleus captures K or L shell electron, an atomic electron. And in this case, when that occurs, a proton is converted into a neutron. And then spontaneous fission, which occurs in some of the heavier actinides, where you will have the isotope splitting. And an example here, it's an asymmetric split. Here's an example of californium going to xenon and ruthenium. However, with fission, there's always a distribution, and here's a plot of some fission distributions where we have fission yield versus mass number. So same thing here, fission yield 7%. Fission yield is a very high fission yield. Mass number here goes from about 80 to 160. And two things we notice here: the high Z peak, high A peak is about the same. This is being dictated by the doubly magic tin 132. And then the low A peak, well, where that peak occurs is going to be based upon which isotope is fissioning. So we can see that the 233 is at the lowest and the plutonium-239 is at the highest. Other thing that's interesting about this peak, if we look at ratios of the elements that are formed, or isotopes that are formed, we can get an idea of the parent fissile isotope. For instance, if we look at the ratio of zirconium to technetium, we follow the green for uranium-233. You see that zirconium divided by technetium would be a number greater than 1. If we looked at uranium-235, they're approximately equal. That number would be very close to 1. And then if we looked at plutonium-239, the technetium is much larger, so that number would be smaller than 1. This is a way of identifying information about the fissile isotope that produced the fission products. And then this figure here, where we're looking at uranium-235 fission, the difference is the neutron energy. And the other thing we see is we increase the neutron energy. This valley definitely decreases. We lose a little bit of the shell model, that direction that forms this double hump. We could even hypothesize that at very high energies, we should see symmetric fission. Okay. Another emission, photon emission, also called gamma decay. Right, there's two types of, there's two occurrences where photon is emitted from something that's related to radioactive decay. We'll talk about both of them now. Gamma decay, It's just the emission of a photon from an excited nucleus. That nucleus can be shown here for plutonium. The plutonium-240 is created. It's at an excited nuclear state. As nature likes to de-excite by emission of a photon, this photon emission does not change the A or the N or the Z of the nucleus. It's just a photon emission, so plutonium-240 goes from an excited state to a ground state. Same thing with technetium-99. M, it's a metastable state, and it will decay to the technetium-99 ground state. X-rays, they're also photons. They tend to be at much lower energy, and this is an electron property. So it's an electron being removed from a lower level, electron coming down, photon emission correlated with that removal. You can also have electrons produced from deacceleration of high energy electrons, XRDs. And we can also, when we have X-ray production, if we bombard a metal with a high energy electron, we can produce X-rays in that method. There's also synchrotron light sources in which electrons are accelerated and held in a ring, and these sources produce X-rays, which we will talk about when we talk about advanced light sources. Here's an example of some X-rays that are produced from removal of K-shell electrons. Electrons coming from the higher level will emit photons while falling to this K-shell. So if we move electrons here, electrons from the L, M, N, etc. shell come down, they will emit characteristic X-rays. Back in 1913, Moseley evaluated this, and he showed that the frequencies are proportional to basically the atomic number. This is what we use today. You do SEM analysis. You're able to determine the element by the X-ray. Okay, so this information, one way that we try to compile information on isotopes is by using the chart of the nuclides. And I have two pictures here of the chart of the nuclides. This is the one from your book. As we see, the chart of nuclides is plotted Z versus N. We plot that out. We can follow it for all isotopes. There's also one, this is from Karlsruhe. Colors are different. Some of the data is fundamentally different. I just wanted to show you this so that you have an idea that there's other chart of the nuclides out. But we'll stick with ours and discuss the data. Both charts will have the same data. All right, so within the chart of the nuclides, you can get information on the chemical element, the nuclide information, for example, spin and parity, information on the fission yield. You can talk about information about the isotopic abundance of stable isotopes. For instance, here we'll see that lithium-6 has 7.59. That means 7.59% of lithium is lithium-6, and 92.41% of lithium is lithium-7, stable lithium. All these grays here are the stable isotopes. We also have this data here for spin and parity. So if we look at hydrogen, 1/2 minus. But if we look at something like, and helium-3 is 1 dash plus, which means 1/2 minus, 1/2 plus, excuse me. Lithium-4 is 2 minus, lithium-5 is 3/2 minus. But if we go over here, helium-4 doesn't have any data here. Any even nucleus, so even number of protons, even number of neutrons, has a 0+ spin and parity. And for simplicity, on the chart of the nuclides, they just do not list that. For radioactive isotopes, all this data can be listed, and we'll discuss that now. For decay modes, if you have an original nucleus, and you want to talk about where it would decay to, an alpha decay goes down 2 this way, beta minus out goes up diagonal 1, right? So this is staying on the same isobar. Beta plus out, or electron capture, goes down this way. You can also use this for looking at types of reactions. Some of these reactions are listed here. So for this one, alpha 3N reaction, an alpha N reaction, alpha 2N reaction, a gamma, and a proton out, so it just goes down one. You can review this. This is useful if we are discussing isotope production, and we can use this as an example. One of the questions we'll talk about, how can you make plutonium-238? We can use this chart to help understand that. Okay, so the data, this is from the legend in the chart of the nuclides. Let's start with the simple. On every first row, there's just information about the chemical element. It has its symbol, the atomic mass, the element name, and something about the thermal neutron absorption cross-section for all the isotopes that compose that element. For stable isotopes, we have, again, the mass, number, and the symbol, the ground state information that was listed there. We also have cross-section information and some abundance information that we'll talk about with some of the other isotopes. So again, for something that's artificially radioactive, here's one, neodymium-147. The spin and parity is listed here. So if it's 5- minus, the spin and parity is 5/2 minus. It has the half-life listed here, which would be in days, D. And then we have some information on the decay mode, beta minus, and then the number behind that is the energy. If it's beta, the value is an MeV. If it's an alpha, it's also an MeV. But if it's a gamma, the value is in keV. So this is 800 keV for the beta minus and 90 keV for the gamma. We also have some cross-section data. These are thermal neutron capture cross-sections and the resonance integral. The resonance integral is basically integrating everything above thermal energies. We also have the beta disintegration energy in MeV. And then over here, this little triangle indicates that this is a fission product from the fission of uranium-235. Now, there are some isotopes that are naturally occurring and radioactive. Their symbol, there's a black bar on them. We saw on some previous pages that tritium falls into this category, carbon-13 falls into this category. Here's an example of lanthanum-138 against the spin and parity, so the spin and parity is 5+. This number here, again, that's since this is naturally occurring, this is the atom percent abundance, so it's 0.09% of all lanthanum is lanthanum-138. Here's listed the half-life, 1 × 10⁻11 years, very long half-life. And again, the decay modes followed by the energy, the cross-section information, and then for some elements, or for some isotopes, we'll have the isotopic mass listed here. For radioactive isotopes, there's similar data. Again, the mass and symbol number, spin and parity. Some isotopes will have, for instance, this lead-210 has the RAD, that's a historic name, radium-D. The half-life, and again, all the same information, the beta decay energies, the gamma decay energies, and then cross-section information. So that's a N-gamma cross-section information. Some isotopes have more than one isomeric state, so a excited state and a ground state. These are listed by the split isotopes. An example here of xenon-129. On the left side, this side is the metastable state, and on the right side is the ground state. The metastable state has a spin and parity of 11/2 minus. The ground state is 1/2 plus. The half-lives differ, about 8.9 days, versus, well, xenon-129 is stable. The ground state's stable, and it is 26.4% of xenon is xenon-129. Again, decay energy, and then cross-section energy. And since this is a stable isotope, the isotopic mass is listed here. Another example of radioactive isotopes where both the metastable and ground state are radioactive, listed here for tellurium-131. Again, the spin and parity, the half-life, the decay modes, beta disintegration energy, and a fission, this triangle here indicating that it is from the fission of uranium-235. Other data that's presented in the chart of the nuclides on the ends here, this is kind of, we can use this also as a review. Here's all the data for the elements. Right, so silver, 107.8, cross-section, the cumulative cross-section information. As we see, as we go from silver, we get different silver isotopes as we go up. But this data here, these are the fission yields for these given isobars. So for instance, if we look at the 99 isobar, the fission of the percentage of uranium-233 when it fissions that forms the 99 isobar, uranium-233 is here, is 4.9%. You see it's not in parentheses, that's for uranium-233. Plutonium-239 is in parentheses. So when plutonium-239 fissions, 6.21% of the time, it'll form the 99 isobar. So you should be able to answer this question for other isobars on the chart of the nuclides. For uranium-233, plutonium-239, for instance, if we look at the 104, about 1% of the time, when uranium-233 fissions, it yields the 104 isobar. And for plutonium-239, it's 6.1% of the time. Similar data is also present for uranium-235. It's on the other side. See, it's just the single data points. So if we wanted to look at the 132, and here's our doubly magic tin 132, 82, and 50. You can even see that it's got slightly darker bars here. 132 occurs 4.31% of the time. Okay, so based upon what we've discussed already on the chart of the nuclides, you should be able to identify isomers, isobars, isotones, and isotopes. For instance, isobars here, we could say that 57, nickel 57, iron 57, cobalt 57, those are isobars of 57. You should be able to identify the daughter from the decay of the following. So if you were given an isotope and look up the chart of the nuclides, you should be able to indicate what is the daughter of that decay. For some bismuth-212 decays with both alpha and beta, and some isotopes, well, lead-208 is stable. You should be able to identify that it is stable. How is carbon-14 naturally produced? Actually, if you read the front section of the chart of the nuclides, you will see that nitrogen-14 is a target. And if you look at nitrogen-14, if a neutron is added to that, you will get nitrogen-15. So if we take a proton away from nitrogen-15, we get carbon-14, so the reaction must be high-energy neutrons hitting, or one of the possible reactions, high-energy neutrons hitting nitrogen-14, that nucleus then emitting a proton. And then you should be able to do something like identify 5 naturally occurring radionuclides with a Z greater or Z less than 84. Those are the isotopes with the black bars. Here's some other questions. You should be able to identify how many stable isotopes does nickel have? What's the spin and parity of a given isotope? how is plutonium-239 made from uranium-238? Well, if you go to the chart of the nuclides, look at uranium-238, and if I added a neutron to that, I'd get uranium-239. And if that uranium-239 sat, it would undergo beta decay to neptunium-239. And then that neptunium-239 undergoes beta decay to plutonium-239. And that's how we can make plutonium-239. From this, what's the half-life of tellurium-130? If I look at tellurium-130, here's the isotopic abundance. Here's the half-life, 6 times 10 to the 20th years. How does it decay? It's got 2 betas. Well, tellurium-130 decays by double beta decay. And what is the cross-section data? Well, there's 2 data sets here. So this is and you see that the tellurium-131 has an isomeric state. So here's the thermal neutron going to the isomeric state, thermal neutron going to the ground state, resonance to the isomeric state, resonance to the ground state. So this information that's presented in the chart of the nuclides, that can be supplemented by data from the table of the isotopes. And this contains actually much more detailed information. You'll get a mass decay scheme, get information about mass excess, particle separation energy, gamma transitions, and some structural information. So let's see what this looks like. If we were to go to, if you download from the web page the table of the isotopes, you'll get, open it up, you'll get something that looks like this. And if I want to find out some information about an isotope, I can either go to the nuclear chart index or the summary. If I click on one of these, I'll get a list of A's, so these isobars. And for instance, let's look at A of 60. So I can go here and click on A of 60. And what this brings me, this will bring up this information here first. It'll show all the A of 60. So let's say I'm interested in finding out information on cobalt-60. Well, I already have some information here. It'll give me the Q value, which is listed here, the information about the half-lives. Looks like I've got a metastable state and a ground state of this isotope. The spin imparities listed here. The neutron and proton separation energies. There's a lot of information available. So if I click on this, if I click the cobalt-60, it'll give me a list of information here on cobalt-60 that include the mass excess, the cross sections, references that I can look up, and then towards the end of this I'll get some gamma decay information. So cobalt-60 decays to nickel-60, and the yields of the yields of the gammas are listed here. So I see that I get 2 gammas, one at 1,332 keV, one at 1,173 keV, and they're each at very close to 100% yield. So how do I get the yield? Well, I take that number and I multiply it. It tells you what number to multiply by. In this case, it's equal to 1. So if I then click on where the cobalt is listed here, it gives me the decay scheme. And here's much more detail on the decay scheme. So I can see that cobalt-60 has a spin and parity of 5+, a half-life of 5.27 years. It decays by beta. It populates this state 99% of the time. We go to this 4+ state, and then that 4+ state will gamma decay to this state, and then that state will then gamma decay. So that's why we get these 2 high energy gamma decays from the decay of cobalt-60. Okay. Other information that you should be able to utilize from the chart of the nuclides is, here's some equations that we'll go over in a little bit more detail. But one thing we should be able to evaluate is something called the decay constant. From this equation, which this is just the definition of half-life, where The number of half-life is just the amount of time it takes for half of the atoms or the mass or the moles of the isotope to disappear. So here's the data for example iodine-131 as a function of time. We use this as just a first-order decay constant, where the number of atoms at any given time is equal to initial e to the minus lambda t. This lambda is the decay constant, and it's equal to log 2 divided by the half-life. So since the chart of the nuclides and the table of the isotope has all the half-life data, we can now calculate the decay constant for any isotope. Okay, and this can be done, as examples are provided here. If I look up some of these isotopes, I presented the data. The decay constant is just log 2 divided by this. I get the decay constants, and one thing I have to remember is the units. If the half-life's in days, the decay constants in days. Generally, we like to have the decay constants in seconds. So if I convert days into seconds or years into seconds, I get decay constants that are listed here. So here's an example of how one would do this calculation. Here's the half-life for selenium-75. Log 2 divided by this gives me this value. And if I say, well, in one day there's 24 hours, and in 1 hour there's 3,600 seconds, I recalculate the decay constant in inverse seconds. And I can use this equation to perform calculations, examples that are listed here. If I have arsenic 66, how much of it will remain after half a second? Both provided here. And I also provided an example for if you have 1 gram of selenium initially, how much will remain after 12 days? Well, the half-life is 5.8 days. So here's my decay constant. I plug in my equation, 1 gram, e to the minus lambda t, and I can get an answer straight from here. And I can use this, it doesn't matter if it's a gram, I can say how many atoms of selenium, how many would I have remain after 12 days? Well, from this, by inspection, I can see that 37.6% of the selenium decays, and I can just solve it. But I can solve it by plugging, as opposed to 1 gram, I can just put in 10,000 atoms. Okay. As a way of closing out this lecture, we want to talk about nuclear force or forces in nature, because there's 4 main forces in nature, right? Gravity, and we're familiar with that. Electromagnetic force. There's 2 forces that actually deal with radioactive decay: the weak interaction and the strong interaction. Say the weak interaction is responsible for beta decay, and the strong interaction is actually something that defines some of the nuclear properties. So for radiochemistry, these 2 forces are somewhat important. And here's a table that kind of gives you an idea of the forces, their relative strengths, and their ranges. As we see, the strong force is basically on the size of the nucleus. The weak interaction is even smaller than that, while gravity and electromagnetic are a little bit further ranged. The boundary of the course that we're going to discuss is really particle physics. We won't go much into particle physics. However, the tools and concepts such as accelerators, which are used for exploring radiochemistry at higher energies, you start understanding particle physics. Well, for particles, they tend to be classified as fermions or bosons. Fermions obey Pauli principle. We're familiar with these. They tend to have half-integer spins. Electrons, protons, and neutrons are fermions. The reason that this is important, as chemists, we're familiar with electron behavior and how electrons behave through the Pauli principle. Neutrons and protons do the same thing. When we get to the shell model, the fact that these neutrons and protons are fermions, like electrons, we can utilize that to understand something about nuclear properties. Bosons, they do not obey the Pauli principle. They have symmetric wave functions and integer spins. An example of that. When we also talk about particle physics, we can explain some aspects of particle physics using the Standard Model. two aspects of the standard models are force carriers, these leptons, and then quarks. One of the things that we want to look up, think about when we talk about quarks is when we think about beta decay, we're often converting either a neutron into a proton or vice versa. You can think about that at a level with the quarks where we actually do interchanging of quarks. Now if I look at the charge, and let's focus on the up quark and the down quark. If I look at their charges, I can see that one up quark and two down quarks, that's 2/3 minus 2/3, that would be 0. So a neutron would be composed of two down quarks and an up quark. Where a proton would be two up quarks, right, plus the negative 1/3, that'd be a charge of 1. So you should be able to use this information, answer questions like, okay, what are the quarks in a neutron and a proton? Okay, so let's review what we went over in this lecture. We defined radiochemistry. We talked about different types of radioactive decay. We discussed the data that's presented in the chart of the nuclides and the table of the isotopes. And we identified things about fission products, photon emission. As a reminder, you should read the introduction to the chart of the nuclides and the table of the isotopes. Here are some examples of questions that you should be able to answer from what we discussed in the course. This was something that we can bring up in our discussion section. And
please comment on this lecture on the blog, and on the web page you'll see the link to the PDF quiz. Please complete that and send it in using the email link on the PDF.